like this. So let's talk about dicarbon, shall we? So this is important to remember that you have to get the number of electrons right. So if you see just this 2s and 2p manifold, we are talking about only valence electrons. So in this case, each carbon has 4 valence electrons. We are giving it a total of 8. Start from the bottom, 2 in each box, work your way up. 2 here, 2 there, 1 there, 2 there, and then, so just like Hund's rule with atoms, when you have a bunch of states with the same energy, occupy them all singly, then pair them up. All right, so, and that is 8. So what's the bond order of dicarbon? Well, we've got 6 bonding electrons, and we have 2 anti-bonding electrons, giving us a bond order of 2. So we would call that a double bond. And that is consistent with experiment, that bond in dicarbon seems to be of a length and strength that one would associate with a double bond, or a carbon double bond in particular. And it has no unpaired electrons, which means it is, and the word we use to describe that is diamagnetic. So dicarbon molecules are weakly repelled by magnetic fields. And the last thing we should be able to figure out is the electron configuration, and it's just like it was for atoms. Just each of these labels followed by an exponent that tells you how many are in each. So it would be sigma 1s2, sigma 2s star 2, and sigma 2p star 4. And that's dicarbon. So let's revisit the molecule that started this entire discussion, oxygen. So remember, oxygen has this ordering for the 2p states, the sigma state and then the pi states. Each oxygen atom has 6 valence electrons for a total of 12. So let's load them up. So 2 here, 2 there, 2 there, that's 6, 7, 8, 9, 10. I apologize, that should have been 1 at a time. We have 2 more, and now it is important to put them in 1 at a time. So 1 here, 1 there. So this explains the experimental observation that O2 actually has 2 unpaired electrons in it. Bond order. So we've got 8, so we've got 4 here, 4 here, 4 here. I'm sorry, 2 here, 4 here, 2 here, 2 here. 8 bonding electrons. We've got 1, 2, 3, 4 anti-bonding electrons for a bond order of 2. Now, this is consistent with Lewis via CPR theory that O2 has a double bond. So, whenever you're proposing a new theory, it is great if your theory explains what the other one did not, but it better had also correctly explained everything that the old theory explained well also. So this prediction of a double bond was good. So if molecular orbital theory had predicted these unpaired electrons, but had predicted a single bond, that would have been a problem. That's not necessarily progress. You know, if that's 1 step forward, 1 step back. But so this actually worked. All right, and that's basically how you work with, you know, you can figure out what's the electron configuration. So electrons. So this is paramagnetic. So paramagnetic is the word we use to describe a molecule that has unpaired electrons in it. And the last thing is the electron configuration. Again, just label the states and then number them. So sigma 2s2, sigma 2s star 2, sigma 2p 2, sigma pi 2p 4, and finally sigma 2p star 2. So now, if I give you the formula of a second row diatomic, you should be able to do this. Figure out what the ordering is, populate each state with the right number of electrons, give me a configuration, give me a bond order, give me a number of unpaired electrons, and remember if it's diamagnetic or paramagnetic. That's pretty much it. 1 more to go.